Hello students, welcome to the heat transfer. With the continuation of module 5, that is, we are going to discuss about the boiling and condensation concept. Here, let us understand what is meant by boiling. You might have already studied in the previous semester in thermodynamics how the steam is generated or vapor formed. So here also we have to understand and analyze the correlation, some of the equations developed by the scientists. So we are to analyze the bubble formation, how the characteristics of the bubble are changed with the various geometrical objects like vertical plate, horizontal plate, like that. So we'll discuss in the coming slides. So first, what is mean by boiling? Boiling is a process of addition of heat to a liquid such a way that generation of vapor occurs, and its solid liquid interface. It is a solid and liquid interface, and it is characterized by rapid formation of vapor bubbles. Actually, during this boiling, the vapor or bubble is formed, and during the evaporation, liquid vapor interface is taking place, and pressure of the vapor is less than pressure of the saturated liquid at a given temperature. During this, there is no bubble formation or bubble motion. So here you can see the picture. So let us 20 or 30 degrees centigrade of water is exposed to the atmosphere, so it is easily evaporates. Okay, next one is how the boiling occurs. So already we discussed that it is a solid liquid interface. When liquid is brought into the contact with the surface at a temperature above the saturation temperature of the liquid. So here suppose coil is provided, so through that the heat is going to be supplied. So when the liquid is received the heat, so it start to changing the phase from liquid to vapor or solid to liquid. So here the temperature at 100 degrees centigrade at saturation temperature, and the coil is having more than that. So due to this temperature, so the liquid the is start to boil at 1 atmospheric pressure. So again, the boiling there are categorized in two ways. One is pool boiling and flow boiling. What is pool boiling? In pool boiling, uh, a fluid is a stationary fluid and motion is due to the natural convection current. So in this case, what happened? The fluid at a static condition, okay, and there is no motion, but the motion is due to the natural convection current and motion of the bubble under the influence of buoyancy effect. Okay, and but in case of flow boiling, the fluid is forced to move in heated pipe or surface by external means of such as pump. Okay, so here we are taking the formation of the bubble. It is the fluid is forced to move with the help of some energy source like pump, but it is always accompanied by the other convection effect. So you can see both the figure and understand how the pool boiling is taking place and the flow boiling is taking place. So boiling classification, again we can classify it as subcooled boiling and saturated boiling. So what happens in subcooled boiling at a 1 atmospheric pressure? So water is having a 80 degrees centigrade. Once it start get the boil or start the heating, so what happened, above 100 degrees centigrade boiling is taking place. Once if it cross the boiling temperature at 1 atmospheric pressure, the bubble will start to boil, start to form. So in this case, the temperature of bulk liquid is less than temperature of the saturated liquid. And in case of saturated boiling, what happened? So the water at a saturation condition, when you give the heat and temperature of the water, that is 100 degrees centigrade, and it start to boil, but here the bulk of the liquid is equals to the saturated liquid of the temperature. Here are the two differences. Next, very important concept, there is a boiling curve for saturated water at atmospheric pressure. In the examination, they may ask, discuss the boiling regimes or conditions, various conditions during the saturated boiling of curve of water at atmospheric pressure. So they may ask for 8 marks theory. So it is very important. So first we have to draw this diagram. Okay, so along the Q and the temperature axis. So along the y-axis temperature, the Q, the rate of heat transfer per area, and here along the x-axis the temperature axis, that is surface temperature minus saturated temperature in terms of degree centigrade. So here initially the boiled water is going to be suppose if it is in a solid state like ice. Okay, if you consider we can consider for this water in such a way that forms. So in this diagram we can understand when the surface of liquid is exposed to atmosphere and it is maintained at a temperature above the saturation temperature of the liquid, the boiling may occur. So, and the heat flux will be depends upon the difference between the temperature of the surface and the saturation temperature. So here when the heat is heated the surface, the submerged below the free surface of liquid, the process is referred as pool boiling, as we discussed. And if the temperature of the fluid is below the saturation temperature, the process is called subcooled or local, or sometimes we also called as boiling. If the liquid is maintained at the saturation temperature, the process we called as saturated or bulk or boiling. So in the figure what we can understand that along the x-axis the temperature, water surface temperature minus saturation temperature, that is we call it as temperature excess, plotted along the x-axis. In this region a free convection currents are responsible for the motion of the fluid near the surface, and in this region the liquid near heated surface is superheated slightly and it is subsequently evaporates when it rises to a surface. Once if the heat is go on increased and it starting from 1 to A, the point we call it as natural convection boiling. So once it reaches that point, and next stage is bubbles collapse in the liquid. Once it start boiling, and because of the temperature excess, what happen? Sometimes the bubble will start collapses in the liquid state itself, and A to B, that is the bubbles collapse in the liquid, and B to C is we call it as nucleate boiling, or we can in this stage what happen, the bubbles rise to the free surfaces. So at the top layer of this water, heated water, that at that point the bubbles are going to be accumulate at that surfaces. So once it reach that point, point C, again what happened? The transition boiling is occurs. Why transition action? Because of it reaches as the maximum temperature or a heat flux. So here again water the vapors decreases the heat transfer, and once it point reach D, again the film boiling is taking place. What is film boiling? Is the accumulation of the at the surface, the bubbles or vapors are accumulated. It is point D to E. So we are consider this point D point we call it as leaden forced point, or at this point Q is minimum. So Q is maximum when it reaches a transition boiling at point C. When it is Q is minimum, it reaches point D at leaden forced point. So this is how we are going to analyze, and based on this some of the relations are there, empirical relations. So let us see how the nucleate boiling. I have put up some pictures, nucleate boiling, how it looks, and transition boiling when the water is get reach transition boiling, and film boiling. So this is the bubbles of vapors accumulated at the surfaces. So now boiling regimes natural convection. One is natural convection. It is governed by the convection currents and heat transfer from the heating surface to the fluid by natural convection. In case of nucleate boiling, stirring and agitation of caused by the entrainment of the liquid to the heater surface is increased. That is heat transfer coefficient and heat flux. So high heat rate transfer are achieved in this nucleate boiling. So in transient boiling, again we can see that the film boiling. So governed by the natural convection current and heat transfer from the heating surface to the liquid by natural convection. So in this film boiling, the presence of vapor film is responsible for the low heat transfer rates. Okay, so heat transfer rate increases with increasing excess temperature, that is delta TE, as a result of heat transfer from the heated surface to the liquid through the vapor film by radiations. Next one is boiling nucleation, boiling inceptions. So here once the boiling nucleation is taking place, the process bubble formation we call it as nucleation, and the surface we can see for the first surface what happened, the trapped pockets of the gases, okay, between the surface and the vapor, and the rough wall will be shown in the below of that water surface liquid. So here what happens, if the crack and creases do not constitute nucleation site for the bubbles, but it contain pockets or gas are trapped or air, okay, it is form of these pockets of trapped air that vapor bubbles begins grown during the nucleate boiling, and these cavities are sites at which bubbles nucleation occurs. Let us understand what is meant by condensation. So already you know condensation is the process in which the removal of heat from the system causes vapor to convert into liquid. Already you have seen an example in a refrigerator, your condenser is there. The process, the working of the condenser is what? So it removal of heat from the fluid, and it is converted into liquid form, vapor form into liquid. Here also the condensation is process is to removal of heat from the system of caused due to the condensation process and vapor to convert into liquid, and important role in nature. First one is a crucial component of the water cycle industry, and the spectrum of the flow process associated with the condensation on solid surface is almost a mirror image of those involved in a boiling, and can also occur in a free surface of a liquid, even in a gas. And this process is numerous, taking place in a multitude situations. And again classification. So mode of condensation is homogeneous, drop wise and film wise and direct contact conditions of the vapor, and single component and multi component with all components condensable, multi component including non condensable components. And system geometry is plane surface, external or internal surface, etc. These are all overlaps among the different classification methods, and classification based on the mode of condensation is the most useful. In further discussion, we can see how the classification they are made. The first one, the mode of condensation. First one is a film is formed. Okay. So second one is film condensation, and second one is drop wise condensation on surfaces. So at the surface, the accumulation of the water droplets are accumulated, so start to condensate. So we call it as drop wise condensation, and the temperature is less than that saturated temperature. And this figure C, we can see that the homogeneous condensation, fog formation resulting from increased pressure due to the expansion. So we can see due to the fog formation due to increase in pressure. And the last one is direct contact condensation. Okay, so vapor is there and liquid spray and droplets. So these are all condensation classifications. Okay, let us understand what is dropwise and filmwise condensation. The surface is blanketed by liquid film of increasing the thickness, and liquid wall offers resistance. So what happened in case of film condensation, the liquid wall itself acts as a resistance. Okay, and this characteristics of clean and uncontaminated surfaces. The next dropwise condensation is what happened. The surface is coated with a substance that inhibits wetting, and drop forms in crack pits and cavities. Typically, it is greater than 90% of the cavities. Okay, the surface is drops and droplets are slides down at a certain size and cleaning and exposing the surfaces. And dropwise condensation, uh, it provides and maintaining the non-wetting surfaces characteristics can be difficult, and the condensate liquid often gradually removes the promoters. And furthermore, the accumulation of the droplets on surface can eventually lead to the formation of the liquid film. So here we have some oscillated heat transfer occurs smaller droplets due to the higher thermal resistance in larger droplets. So enthalpy, okay, drop wide condensation is equal to 51,104 plus 2044 T saturated temperature. So together the enthalpy of condensation 2,55,510. So here what happened, the 22 degrees centigrade is less than saturation temperature, and it is again less than 100 degrees centigrade. So obviously the 100 degrees centigrade is less than the saturation temperature. The laminar film condensation. So laminar film condensation, here are the figures. So how the layers are of the laminar regimes are found here. The mass at inlet, and when it is come out to the out, if for elemental film we are consider, and m plus dhm. Okay, and again the dq is equals to hfg into dh. So again when it is come out and it becomes heat transfer q double dash b plus dx. So this is how the elemental analysis is going to be taken place, and here some velocity boundary layers are formed. So we can observe in liquid stage the velocity boundary layer are occurred uh, at the surface to the of the liquid and the wall. So even we can see in the thermal boundary in the system and the figure. So now we have to analyze the Nusselt integral analysis. Okay, so while understanding the concept or any of the analysis of the liquid or fluid of condensation or boiling, so some of the assumptions are made. Here also the scientists Nusselt have given some assumptions. So first one is laminar flow and constant process properties, and second one is gas is assumed to be pure vapor and in uniform saturation temperature, and third one is the shear stress at the liquid vapor interface is negligible, that is dou u by dou y at y is equal to delta is equal to 0, and momentum and energy transfer by advection in the condensate film are assumed to be negligible. So these are some assumptions are made while relating the equations. So Reynolds number at delta is equal to 4 tau divided by mu into L. So where condensate mass flow rate as m, that is rho L um and b delta, where Reynolds number delta is equal to 4m divided by mu L into b. Okay, further we can understand for the turbulent film condensation. So again the relations are made. So these relations are available in the heat transfer. So based on the condition of the from this condition of the problem, we have to use the chart and find out the equations. Okay, here are the some formulas available heat transfer data handbook along with the charts. Okay, here the turbulent film condensation, so various Reynolds number along with the heat transfer coefficient of that fluid, we have to choose the formula and solve the problems. So next one is, so different film condensation on different geometry object. One is sphere and single horizontal tube, vertical tire of the horizontal tube with continuous of condensate sheet, and last one is dripping of condensate. So these are all film condensation at various geometry. Okay, students, based on this theory concept, we can solve the problems. And in the heat transfer data handbook, there are some correlation they have given of the boiling and condensation concept. So we have to refer and solve the problem. Thanks for watching this video.